So, what we so far I taught two topics. One is the power plant cycle analysis, thermodynamic cycle analysis of all power generation, mainly thermal power generation, and second one is the components of power plant cycle. The third topic is as you know, the first topic, that is power plant cycle analysis. In power plant cycle analysis, we dealt with mainly first law point of view. So, therefore, in first law of thermodynamics, it gives only the conversion from one form to the other, but it does not give you the quality of conversion. So, therefore, it is important to analyze second law of thermodynamics also for the cycles. Anyhow, I will ask Natraj to give some papers related to this on not only second law analysis, but also economic and environment analysis of a power plant cycle. We published earlier some papers, but that will be mainly your course is only till second law, but that is an additional information. Those who are really interested, they can go through that also. So, why perhaps you studied in your thermodynamics or and applied thermodynamics that the importance of second law. So, we will look at how the second law is important in this case. Actually, I have already mentioned that the first law of thermodynamics deals with the quantity of energy and asserts that energy cannot be created or destroyed, and this law mainly serves as a necessary tool for bookkeeping of energy during the process, during any process or so. Therefore, it is important to come up with the second law. This second law deals with the quality of energy. So, generally the quality is there are several words to several terms to the quality of energy that we will discuss in detail which terminology is to be used, but generally this quality of energy is in terms of a word called exergy. There are other terms like availability, SRG, energy and so on, but exergy is the most widely accepted word of second law analysis. So, generally this quality of energy is that it is concerned with the degradation of energy during the process and the entropy generation and the last opportunity to do the work. Okay. So, you can see here. Before that, I will give you some small examples so that you can understand what is the importance of exergy. So, there are different forms of energy, is not it? So, what form of energy you have now? What you are sitting in the class, what form of energy you have? Huh? Potential energy. What is your potential energy now? How do you find out? Huh? Huh? Okay, mgh. So, you know m and g. What is a h? Now, here for example, for you what is a h? You are in second floor of building, is not it? How many meters it will be? Approximately, no? Huh? 6 meters. So, our other friends in Kathmandu, they are also perhaps in the same room, they are listening to us. Okay. What is their potential? You are in which floor? No, one of you. I am. You are different location.
Because there is holidays in the university of this because of this Chhat Parva.
So
we are at different locations.
Okay. So now, for example, this is Nukula. Who is speaking?
It's Gaurav, sir.
It's Gaurav. So Gaurav, where are you now sitting in?
First floor, sir.
First floor. Okay. First floor. So suppose assume that, see here the students who are in front of me are there in second floor. Suppose if you are in second floor, same second floor, assume, then what is potential energy? So what is
Mass multiplied through gravity and height.
height? So height is assume that every floor is about 3.5 meters. So about 7 meters height. Okay,
Yes, sir.
7 meters height you are. So both there also 7 meters height. So what is the potential energy, is the same or different? You are
Both are at 7-meter height, sir.
so you are also in second floor, and here students who are in 7 meters height here.
Sir, if the masses are same and gravities are same, then I think potential will be same.
Okay, same. So that is as far as the first law is concerned. Okay. But as far as the first law is concerned, potential energy, when you have a height of 7 meters from the reference point, that is a datum, it is same, because that is a potential energy which you carry that, or which you have, which you. Suppose as per the second law of thermodynamics concerned, it is not the same. Okay. Suppose if you have to define as per the second law of thermodynamics, what is the potential energy? What is your potential energy? And there,
That's what second law of thermodynamics.
so then we have to, in second law of thermodynamics, we have to look at the what is the dead state or reference state. What is generally altitude is measured in what, height of height measured in terms of what, with reference to what, mean sea level. So now if you look at mean sea level, so you are maybe Chennai is about 50 feet or something, is close to, so maybe you are somewhere in 2000 meters or beyond. I do not know how, what is your altitude?
Around same, sir, 2000 to 1800.
To 1800 altitude. So now if you look at second law, it is 7 meters plus 2000, whereas in case of here it is. So therefore, as far as the second law is concerned, the quality of,
It's a point function.
no, it is a reference case, that is called dead state. Dead means what is the dead state, with reference to dead state, what is the energy which you possess. Okay. So then you can see that what is the irreversibility, how much, what is the available energy, you can find out. This is a simple example of potential energy. So similarly, for everything you can define same way for other forms of energy also. Okay. So therefore now I hope you understood what is the difference here. So therefore if you bring both the places to the same level, what happens is one will be somewhere here and another one here. But practically first law is concerned, both are same, second law is a difference. So that is a basic example of second law of thermodynamics. So now that is what we define availability, exergy, the maximum work potential. See, the availability means maximum work. See, your maximum work potentially of potential energy is different from that of you are who located here. So therefore this second law analysis tells you that what is the maximum work potential, out of which how much you can convert into useful form. So therefore now we have energy efficiency, there is the exergy efficiency also. So therefore in any process you can find out what is the irreversibility, how to avoid irreversibility, that we generally define in this. So here I have given a system, here. I have given a closed system which is E, and the system boundary is this, and there is a heat and work interaction between the system and the environment, and boundary of the combined system is this, and there is only interactions are allowed with the total volume is this here. So the system will deliver maximum possible work as it undergoes reversible process from the specified initial state to the state of its environment, which is called dead state. Just now I mentioned your dead state with respect to potential energy is mean sea level. Okay. So, but when you are comparing with 7 meter height, means it is with reference to the local state, local reference case, local data. So, therefore, any energy which is any form of energy which is defined with reference to dead state, it is called availability or exergy. There are other forms also, I will tell. The energy is there because it is a chemical potential also we consider. Suppose if some fuel is there, so coal you are burning, what is the exergetic efficiency of a fuel conversion? See, combustion is a simple transformation. The typical classic example for exergy is for example, now I have given you the potential energy. Suppose you take have you studied this OTEC, ocean energy thermal conversion? Ocean energy thermal conversion means, but I think that see you have a heat engine, then there is a heat engine and it takes at T1 and W here and Q1, Q2 and T2. So, this is one type of engine. The another engine is there. This Q1 is there, but the temperature is something maybe temperature of A. Here the Q1s are equal, but the temperatures are different. So, for example, so 1 kg of coal you burn it, okay, 1 kg of coal. Or another example is suppose you have a power plant, this is about 500 megawatts of heat is supplied to an engine at temperature of, what is a coal power plant temperature typical? You have already studied, maximum is 575 degrees in supercritical power plant. Okay. So, now I have same 500 megawatts of heat, but this temperature is about 35 degrees. Heat is same. Which engine will have a higher efficiency? Heat inputs are same. Whatever thermal means first law efficiency. As far as first law is concerned, second law is concerned, this is better, but we have not discussed yet about second law now. So, now as far as, see, now heat inputs are same for the same engine, but they are different temperature. As far as the first law is concerned, it should give the same. Sink temperature is same, sink temperature same, I assume that may be marginally different. Okay. So, so assume that it is about 25 degrees, this is also 25 degrees. So, as far as the first law is concerned, or otherwise I will tell that this is about 4 degrees Celsius, this is also 4 degrees Celsius. Okay. So, as far as the first law is concerned, it is supposed to be both supposed to be same, because when the heat is, but actually it is not. The second law tells you that the quality of heat, the 500 megawatts though it is same, but the quality of heat is different. So, therefore, when you have a higher quality of heat, obviously you will have a higher capability to do work. Okay. So, therefore, that is the essential gist of the second law of thermodynamics. Okay. Generally what we do is classic example for this is OTEC. But anyhow I will give you OTEC. What is OTEC? OTEC, ocean thermal energy conversion. Ocean thermal energy conversion means you have a sea or ocean, Bay of Bengal or something, then you are here, this is the sea, go to Marina Beach or somewhere. What is the temperature of the sea, surface temperature? Surface temperature of the sea is somewhere, assume that it is generally be equivalent to atmospheric temperature, but what happens is there is a evaporative cooling, you know evaporative cooling. So, because of that it may be slightly lower than this. So, then you have assume that summer temperature outside you have 45 and this is about 35 degrees Celsius. So, now here, and if you go deep here down about 4 or 5 kilometers deeper, what is the temperature of the water? That will be somewhere about 5 degrees Celsius. If you go deep into that, about 5 kilometers deep or 4 kilometers deep, then you construct a engine, take this is the source and this is the sink. Can you construct an engine here? So, it takes Q1 from here and Q2, it rejects Q2 into the deeper sea water. So, what is Q1? Q1 is at the heat at the surface of the water, sea water. So, how do you find out Q of water at the surface? How much heat? This is nothing but MCPT, MCPT of T is 35, Cp of water 4.18, and what is the mass? Mass of the sea water? Oh, mass of the sea water is it's huge. So, but infinite, and if you multiply this infinite into Cp into T, what is the Q1? Infinite. Or otherwise you consider, no sir, that infinite C I do not want to consider, I consider some 10 square kilometers of water, not deeper inside. Or 10 square kilometer means what is the mass of that water in the 10 square kilometer, and you can find out. Assume that again it is a 500 megawatts of heat. So, therefore, this 500 megawatts of heat is supplied to this engine and it is rejecting at 4 degrees Celsius, 5 degrees Celsius to this one. So, now this efficiency of this, we have seen here the temperature is very low, but the amount of heat is very high. So, same 500 megawatts of heat if you produce by burning of coal and same engine is used to convert the heat into work, obviously the coal based power plant will have a higher efficiency than this. This is the basic comparison how a first law works and second law works. Okay. So, therefore, I hope now you understood what is the. So, then generally ocean thermal energy conversion system is the reference case for second law analysis. So, you know how much efficiency it will give? Can you guess? Same 500 megawatts and all. If it is based on coal, how much it will be? 35%. By this you will get 0.5%. So, maximum 1%, not more than that. Okay. So, that is why then some power plants have been installed based on this, because this Q, though it is infinite, it is free, whereas here you are burning fuel. You got my point. So, that is the concept came, but I think there are only few OTEC power plants are built. So, now I hope you understood real. So, this is another way of presenting that heat and work. Heat is less quality of work, less quality of energy, and work is more higher. That is why conversion of work to heat is 100%, but the reverse is not possible. So, you got my, when we write in first law, the work also we write in terms of megawatt, watts only, conversion, correct. So, therefore, that is the difference. So, now I hope this is a simple introduction why we go for second law of thermodynamic analysis. So, the dead state, and this represents the useful work potential of a system at a specified state is called availability, okay, called availability. Now, this there is a reversible work. This is the amount of useful work that can be obtained as a system undergoes a process between the specified initial and final states is called reversible work, and irreversibility means any difference between reversible work and the useful work is due to irreversibility present during the process. So, now irreversibility term I dot is given by W irreversible dot minus W u dot. Second law efficiency, which is also known as effectiveness, it is a ratio of actual thermal efficiency to maximum possible, that is a reversible thermal efficiency under the same conditions. So, how do we define second law is like this. So, second law efficiency is equal to eta thermal by eta thermal irreversible. Irreversible efficiency is supposed to be the highest efficiency. So, now if you have to convert potential energy, what is the second law efficiency as far as potential energy for example, you construct a hydroelectric plant in this 7 meters height and same plant in Nepal. So, if first law will give you same output, but whereas second law is this. So, the maximum in here also second law efficiency means potential energy difference between this two reference case divided by from that to main sea level, okay. That is the difference. So, the maximum available work which we refer it as exergy. Now, I am giving you some assumption here. See, consider this heat source at TH and it gives T as this is the engine and which converts into work, and then it rejects at TL. TL means a low temperature to the cold sink. In this case the engine operates between TH and TL, and then QH is equal to AE plus UE, here available energy plus utilization energy, that is useful energy. So, W max is equal to maximum W max is equal to available energy, which is QH minus UE. So, therefore, the maximum attainable efficiency for a reversible cycle is this. Reversible cycle is 1 minus TH by TL, which you know that this one you know 1 minus T2 by T1. But what is the maximum work? Maximum work is given by, this is the reversible efficiency. Reversible efficiency into QH is the maximum work. So, what is the difference between these two is, as for first law is actual work, this is a spelling mistake, actual work to QH is the first law efficiency, So, first law efficiency can be represented as this Roman eta I and eta 1 and eta 2, or you can write 1 and 2 like that also. Sometimes what it is represented is first law is represented as eta and second law represented as epsilon, effectiveness. Epsilon means effectiveness. So, this is given by this actual work to the exergy, that is W max, which is given by this. So, therefore, this is the one eta 1 by 1 minus T h by T. This is wrong, is not it? It is a reverse, sorry. This is some typo error. Sorry, this is a TL by TH. TL by TH. This you please correct. This is some typo issue. Then I'll give you. I hope now what is the rest I can explain easily. Once you understand what is the basic concept behind that, then you can do this. So, exergy is defined as exergy is equal to energy minus energy. This is a new term which I am giving here, energy. Exergy, have you heard before exergy? Some of you have heard, isn't it? So, but now this is a new term. Exergy is the maximum work obtainable as the system comes to equilibrium with the surroundings. Higher the value of exergy, that means more is the work obtainable from the system. So, again this I mentioned as well. First law of thermodynamics makes only energy balance of the system or a control volume, but it does not make any distinction of different forms of energy, particularly between the work and heat or heat available at different temperatures, which I have already explained. So, that temperature at different this thing, whereas the second law is a engineering point of view, all forms of energies are not of the same quality. So, therefore, energies of two systems may be quantitatively equal, but qualitatively they are different. Just now I explained. So, 500 megawatts is quantitatively same, but qualitatively 500 megawatt 35 degrees is different from that of 575. So, therefore, the exergy is a measure of energy quality, and exergetic efficiency is a measure of the perfectness of thermal system. So, therefore, the energy system in any process remain constant, part of its exergy is always destroyed. This is the meaning of that. So, now I for example, will take a turbine case. You have studied all first law of thermodynamics as a steady flow energy equations. So, the 4 components will take steady flow energy equation, perhaps you applied for boilers, turbines, pumps and condenser. So, for example, here consider a turbine whose enthalpy entropies are given here, but here generally we represent 2 to 1 and 1 to 2, but here it is 2 and 1, because this is a kind of a reverse thing. So, so here why, because 2 is referred as at higher level, that is the meaning of that, but do not worry about this notation. The available work or exergy delivered by the flow system is equal to the net flow exergy into the system. In fact, we have done detailed exergetic analysis for large scale power generation, that is what I will ask Nataraj to share the papers which are related. We started this exergy analysis way back, some 15 years back. Most of these thermal power plants were studied with respect to exergy energy analysis and environment and economic analysis, and some case studies also we did. It's like North Chennai thermal power plant and even Ramagundam thermal power plant we did it. So that what happens is, if you do exergetic analysis of a power generation, you will come to know where are the irreversibilities, so that you can focus on that particular part. Okay. If the heat rejection is the major problem, then you focus on heat rejection, try to improve the efficiency of that. So, because in a cycle, the working fluid undergoes cyclic process in different processes and different components and different passages. Passage means it takes such a long time. So, suppose if you take a thermal power plant, the pipelines of several kilometers. It is not that we generally represent Rankine cycle as 4 components, but if you look at real power plant, I also explained the real power plant is not such a simple one complex with the regenerators, reheaters and feed water heaters, and when this working fluid undergoes a process cyclic process, there will be interaction with all these components. So, now this is one actually the net flow exergy into the system, that means via heat transfer and fluid flow minus the exergy destroyed through thermodynamic irreversibility is referred as a exergy delivered. And then to explain the flow exergy, we need to understand the property called flow availability B, and the flow availability is given by H. H is the enthalpy minus T naught S. S is the entropy, T is the temperature, and the flow exergy is given by B minus B naught. So, B is the availability. Availability is defined with reference to normal availability and with reference to dead state availability. So, B naught is the dead state availability. Okay. So, therefore, B minus B naught is equal to H minus H naught minus H naught T naught into S minus S naught. So, this is the exergy is defined in this way. So, now this I have mentioned, no, the exergy calculations change when the environment condition change, because see when just now I asked you what is the potential energy. So, then what is your other forms of energy at this location, means what is your internal energy, okay, and what is the thermal energy. Okay, these all energies need to be summed up and considered as a single energy. So, now for maximum available flow from a flow stream like this, you can see turbine, and it is given by this. I have taken a generalized equation, W max is equal to summation of exergy in minus summation of exergy out. So, the number of exergies in minus number of exergies out. So, here exergy E x is the specific exergy. If you multiply with mass, so you have seen capital H and small h. Small h is the specific enthalpy, capital H is the total enthalpy. So, same way, so mass flow rate into E x minus mass flow rate at out, which is given by this equation here. So, here the mass flow rate is, there is mass flow is conserved here. So, therefore, m dot is the same. So, then you can rewrite this in this form. Okay. So, where this E x is the flow exergy per unit mass, flow exergy per unit mass. So, then what is the difference between exergy to energy? How do we combine first law and second law? Generally, there is a debate, I think, because we have not discussed yet, but generally whether to do second law of thermodynamics or second law of thermodynamic analysis, whether is it necessary to do first law also. Okay. Generally it is required. So, you do a first law, then only you can compare with second law. So, therefore, to identify irreversibilities and so on, so you need to know this. So, therefore, how do we combine this here? The first law of thermodynamics is energy balance, second law of thermodynamics is entropy balance, and this is given by d E by dt is equal to sigma q I minus W dot minus plus this is in minus out. the energy in minus energy out, and the entropy is given by ds dt minus this is q by t is the again S minus W plus this specific entropy in minus entropy out. So, then if you equate Q's available energy from equation 1 and 2, then the exergy of the system is given by this equation. If you write Q UA means available, and A subscript means available or availability. Sorry. So, this rearranging this, so I am not reading out this, anyhow I am going to give this here, and exergy for steady flow means whatever mass is conserved, mass whatever is entering and it is going on. So, it is a steady flow, then this is the same. So, some terms are gone here. So, this I have already mentioned, Ex is the flow exergy per unit mass, or Ex is absolute exergy. Then how the significance, what is the significance if you look at that this term, the energy exergy which is that means the last available work in the same equation, what is the significance means this is the maximum available work and this is the one work is lost because of the dead state. So, here it means whenever a system operates irreversibly, it destroys work at rate that is proportional to the system's rate of entropy generation. So, therefore, W is equal to W reverse minus T naught S gen, that is entropy generation. So, then the exergy loss is which is represented by irreversibility is equal to T naught S gen, that is entropy generation, and this I have already explained. Energy is always conserved, and what is not conserved is exergy. So, that means useful work potential of energy. So, exergy means useful work potential of energy, and exergy is that once exergy is wasted it never be recovered. Yeah.
Why is exergy loss irreversible? Is exergy loss actually irreversible?
Exergy loss is irreversible.
Why do we represent exergy loss?
That means you cannot recover from the see once you are lost you cannot recover it. So, that is why see now again the classic example here is that potential energy I have defined. No? So, now whether really you can see this one is here, another here, the dead state is here. Okay. So, what is this potential and what is this potential? Okay. But you have to bring this to this level, then only you can convert this. You got my point. That means as far as potential energy is concerned, you have to equate to that, and that means when you operate to the dead state, then only it is conserved, otherwise it cannot be. So, that is the meaning of this. Then if you consider simple, I will explain you in detail with each component we are taking in a power plant cycle. Simple Rankine cycle power plant, you have 4 components here. You have this is the same which we discussed in the previous case here. QH is given at TH, this is and you have a turbine, you have a condenser and then pump. This is the cycle, undergoes cycle, and 1 to 2 is pump, 2 to 3 is heat addition, 3 to 4 is expansion, and 4 to 1 is heat rejection. These are all mentioned here. So, now this exergy analysis of this, if you do it for each component of a power plant cycle, to determine the distribution of irreversibility among the cycle components, and so they are operated T naught and T h here, not T L. So, if you whether you define T L or T naught, that is important. So, here they are positive values. Now, for example, if you look at exergy of a combustion process, it is a chemical reaction. Generally what we do is combustion means how do you find out energy of combustion? It is a calorific value. If you burn fuel, it will be a calorific value, is not it? So, but exergy is different. So, now here it is a chemical reactive system, and you have to look at the standard Gibbs function, which is here changer, which is given by this equation, and change of enthalpy of formation is this. This is a minus NCV, that is a net calorific value, and we are defining a function, this Gibbs function, the delta. You perhaps you studied this in your thermodynamics. So, now delta H naught is this MF into NCV, that is a calorific value. So, if MF is that mass of fuel burning rate, therefore, now how you are defining G delta G naught is this way. So, rate of exergy loss in combustion reaction is given by this mass of fuel, calorific value at that, Gibbs function minus 1. That is the, now you ask for loss, this is the last term. Whereas combustion, if you look at combustion, you say what is the heat means only just mass into calorific value, but the total energy which is capable to do work is this actually, this is the loss and then rest, you understand. So, these are some of the examples for different Gibbs function for different fuels here, they are not same. See, in fact, when we do solar energy, solar power plant exergy analysis also we do, you know that. What is the source of solar energy? Sun. What is the temperature of sun? You can see how much conversion, you understand. Then if you look at the exergy point of view, it is a completely different exergy function, but we generally look at only energy point of view. So, therefore, that is why now we are trying to develop more efficient technologies. See, the solar panel which used to work 10 years back is different, now it is different, because we want to convert every joule of energy into useful form, you understand. Tomorrow I think we are talking about this, no, waves, gravity waves. Gravity is now recently, no, it is defined as a wave. So, then when you have a wave, why do not you convert wave energy? So, therefore, I do not know, maybe tomorrow after 50 years somebody can invent a device which converts this atmospheric energy. So, there is no need to burn coal or anything. Now, lot of technological developments are taking place. So, ultimately, see, this is the response, this is how we have to analyze, so that you will come to know where is the, otherwise if you do simple first law, you do not know anything actually. So, this is the meaning of that. Then for example, now we have taken combustion, but the combustion as an input which is given to the boiler or heater, in that case how if you write energy exergy balance, it will be given by this EQH plus this is exergy in minus exergy, and this is the last term which just now we discussed, this is the loss of availability. or destroyed exergy. So, therefore, this energy in and energy out minus destroyed energy. So, therefore, rate of exergy loss in heater is given by this equation. So, this is the equation which sorry. So, I am so now here the part of exergy flow rate entering heater, this is general partially destroyed to inherent irreversibility of boilers. The major source of exergy distraction in power plant cycle is identified as a boiler. So, the boiler is generally referred as a more efficient because you have a see now what is the boiler efficiency? Generally 80%, 90% thermal efficiency, but second law point of view it is inefficient. Why? Because for example, what is the combustion temperature? It is somewhere 1800 degrees Celsius or 1500 to. What is the energy temperature of the steam? It is about 550 degrees Celsius or 575 which we saw. So, 1500 to 550, that is the gap irreversibility, huge irreversibility. But in first law we generally simply that MCV and then you say what is the enthalpy change in this and we will see what is the total. So, therefore, the boiler is a major source of irreversibility. Then how do we minimize? As you know that one of them is a regeneration no, and air preheater and so on. So, every joule of energy is recovered. Again this one, the major source of exergy distraction in power plant is this boiler, but it is critical to use fuel that meets the original specifications for optimum combustion. So, the meaning of that is the coal combustion is a tricky thing. Why? Because Indian coals have different composition, foreign coals have different composition. Indian coals contains high hash and foreign coals have high sulfur. Okay. So, therefore, generally we discuss Indian coals are energy point of view they are bad, but environment point of view it is good because Indian coals contains only 0.5% sulfur. So, therefore, this CO2 leaving combustor provides always some information for effective combustion of significant benefits of energy savings. Then next one is the turbine. It is a turbine is again similar way we have to write the exergy balance is given by exergy in minus exergy, then the exergy lost. So, that is the one here. Then this you can write in terms of enthalpies. So, now you have seen the difference between the energy and exergy. So, the potential energy, again I will come back to potential energy. Potential energy of U, first law point of view mgh, H is whatever you have, but second law is mgh naught, that H naught means here with reference to data. So, what is the conversion between these here is this, see this term, because here mgh with the datum here, I think it is not correct thing to write here, but I will write in terms of enthalpy here. Enthalpy is here. So, you have enthalpy H3, here H4. If energy point of view same H3 H4, but whereas second law of exergy point of view here is H3 plus T, this is Ts3, this is the one here, and here similarly the other one. So, therefore, if you can separate it, it is like this. Though heat transfer exergy is for the turbine is the heat transfer exergy is 0. So, therefore, the turbine converts its exergy input E ME x3 into shaft work, and the remaining fraction is either passed on to the condenser or lost through the irreversibility. Irreversibility means you have turbine here, just I have shown here, this is a 3 part and 4 part here. So, now m dot into H3, this is m dot into H4, then you have the m dot T H3, this one m dot this. So, therefore, this loss, this term, these two terms are with reference to dead state. So, therefore, either they go into the condenser or they are lost because of imperfect insulation, because it is supposed to be isentropic process. Isentropic means reversible adiabatic. Reversible adiabatic means the heat Q is 0, but in turbine you cannot have Q is 0. So, that is the thing. So, therefore, the rate of exergy loss in steam turbine is given by this one, and the last one is the exergy analysis of condenser. It is the same as the boiler. So, condenser is the same equation is used, and then exergy loss in condenser is given by the same equation here. So, here Q2 is the heat rejected into the atmosphere from the condenser at temperature T2, but Q naught is the rate of heat loss to the environment. This Q naught is if you look at condenser, you know condenser is a heat exchanger. Sorry. So, one stream is going here, another stream comes. So, see, this temperature difference plays an important role as far as the heat transfer, but if you define with respect to dead state, dead temperature, environment, this is in condenser you do not consider as an environment, you consider as a whatever the cooling water side. If you consider environment, then you have this rate of heat loss due to environment. So, therefore, heat transfer of exergy 0 for condenser. So, therefore, condenser discharges significant portion of stream of exergy because of heat transfer across the finite temperature difference between the condenser and the ambient. You understand this? What is the meaning of this is, see, just now we discussed boiler. Boiler is from 1800 to 575, but in condenser you know Q2, Q1, Q2 and W. So, Q from Q1, Q2 is almost 2/3 of the Q1. The heat rejected into the condenser, into the atmosphere is almost, because the remaining 1/3 is work. So, that means when you are too much rejecting, obviously you have an enormous irreversibility there. So, therefore, the way in which the heat input, where you have a irreversibility, same way here also you have lot of irreversibility here. Q0 is suppose now ambient temperature. Ambient temperature means here what is the ambient temperature generally? No, ambient means temperature which you measure outside, correct. But now suppose if you are rejecting the heat into the atmosphere, ambient temperature you can consider, but you are rejecting heat into the water body, you have to consider that. Just now I explained here, suppose this is T1, T2, that means this is a hot fluid in condenser, TH in minus TH out, this is TC I minus TC out. The cold fluid is hot fluid and cold fluid. Hot fluid here is a working fluid, steam is getting condensed to this, but circulating water you are sending in a from the cooling. But now this is about performance, but actually this you are taking and putting another heat exchanger. What is that heat exchanger? Cooling tower. See, this you are taking heat and then rejecting into the atmosphere. When you look at with what is the temperature at which it is rejected at the atmosphere, and what is the temperature at which the condenser is rejecting, then that is the difference. This is a Q naught. You got my point. Suppose the ambient temperature is this, but TC out is not the same as TA. Suppose if you look at this delta T between TC TH1 minus this is I will tell. So if you take this delta T and if you take this delta T, okay, delta T H and delta T cold. Now here delta T ambient is there. So if you write with respect to this, that is the difference, and with respect to these two. Generally condenser is heat rejection is based on this, that is why 2/3 of heat is rejected. Whereas this now you ask for Q naught. Q naught is if you write the Q naught with respect to this heat to the heat which is rejected into the atmosphere. So therefore what happens is in most of the cases power plants the heat rejection differs from morning to evening, and most of European power plants are more efficient than Indian. Why? Because the sink temperature is that Q naught is low, you understand. So that is a difference. And I do not know, I have shown you one Netherlands Altac, it is a 53% or something like. So energy balance here for the pump, the pump is same as that what we discussed for turbine, is similar to exactly same. These two are same and these two are same. The difference is one is at higher in case of boiler and condenser, one is at higher temperature, the other one is a lower temperature. Then pump is compressing, the other one is expanding. So the same is the same as the turbine, the rate of exergy loss in feed pump is the same m dot T naught into S1 minus S2 is the same thing. But I think I have also given this for gas turbine also, though we have not taught gas. I think in combined power plants we discussed gas turbine, combined steam and gas turbine plants generally, and we have also discussed binary power plants. Binary means using different working fluids, mercury and water, mercury and sulfur dioxide and so on. So if it is a compressor not a pump, and in a gas turbine power plant the rate of dissipation of irreversibility in the compressor is given by this equation. So what is the difference between Rankine cycle is steam means pure substance, whereas this is ideal gas. So you have to use ideal gas equations here. So this is the ideal gas equation. So then you can find out isentropic efficiency, which we already discussed. The turbine exergy loss is given by this equation m dot T naught S4 minus S3, and that S4 and S3 are in ideal gas conditions. So, this is the equation for ideal gas thing. So, now you can see the difference between how the gas turbine based plants, exergy analysis of gas turbine as well as exergy analysis of Rankine cycle. Suppose if you want to find out total rate of exergy loss in the plant, all combination of everything. So, you can put all of them sigma of all. Why I have taken gas turbine? Because as you know that gas turbine is a combined power plant. Gas turbine is you have seen this, and then you have a so this whatever heat lost in this is gained by this, and the heat supplied is Q1 is here and heat rejected is here. So, this we discussed as a part of combined power plants. So, therefore, it is a combination of compressor, combustion, gas turbine, HRSG. What is HRSG? This is HRSG is this part. Heat recovery steam generator. HRSG means heat recovery steam generator. And then exhaust, some part is gone to atmosphere exhaust, then steam turbine irreversibility, then condenser, then feed pump, and so on, whatever you have many. It is a total exergy loss in complete plant, you have to see that, and then come up with finally total exergy input, that is Gibbs function into the enthalpy. Then you have rate of power generation is both turbine power as gas turbine power plus steam turbine power output, and the exergy efficiency is total rate of exergy output by total rate of exergy input. So, this is the exergetic efficiency, whereas energetic efficiency is what? WGT plus WST by Q1, that is what we discussed. But this is not Q1, this is this in case of exergetic. I have given some example here. This is a combined gas turbine and steam turbine plant. Anyhow, I will give you this to you. So, it is like this, they are connected in series here. So, the air is taken from the atmosphere by compressor, and then some combustion heat is added in combustion. After expansion it goes to the stack, and this is the Rankine cycle with the temperatures, pressures are given here. The turbine output is 102.6 megawatts with 45% efficiency, whereas steam turbine is 34 megawatts. So, in a combined power plant you have a smaller steam turbine, bigger gas turbine plant, and this is HS heat recovery steam generator, this entire part. What is the efficiency of this? The efficiency of this is 34 plus 102.6 by 228. This 228 is the one. But you see here this 102 is not correct. This is 102 by this. In this it is 68.4. This is a net work output is 68.6 plus 34. So, that is the total work output, but you have this is a net, but what is the energy supplied to the compressor is again a different thing. So, therefore, we look at net to net. Then if you give the difference between exergy and energy analysis of all these turbines, and I come up with a, what is this diagram? Have you heard of these diagrams? See, generally if you have done experiments in IC engines, correct?
Online.
Online, oh, that is too much. So, online, have you come up with a heat balance? Then how do you represent graphically?
They gave us like heat release, intake temperature.
So, generally graphical representation is called pie charts. Have you heard of pie charts?
We didn't plot by we did only like line.
But that is only just quantities, but generally suppose if you have some 100% quantity, how this 100% of heat is distributed in combustion chamber, this generally pie charts are used. You know pie charts? Then a circular one, then you put this entire circle is 100%, what is the last in exhaust, what is the conversion in this, like this. So, this is called Sankey diagram. This is also similar to that, but it is represented in different way. It is a Sankey diagram. So, Sankey means if you give 100%, how this 100% is being distributed into various other forms. So, if 100% Q is heat is supplied, then gas turbine is 31%, some loss is 0.6%, steam turbine is 14.9%, this condenser is 28.3%. These are first law efficiencies. Stack means the heat carried away by the flue gases is this and some flue gas losses, these are smaller losses, HR SG is losses. This is with respect to first law energy flows, whereas you have exergy in this, how you can see the difference here. See, the condenser is only 1.4%, whereas in energy point of view this is 28.3%. Heat recovery steam generator is only 0.2%, whereas here 6.9%. So, this is how you come up with the different structure. So, then what you can do is how to minimize these losses. Suppose here you can see that these are unaccounted losses. Now, you come up with some unaccounted losses, you will find out in IC engine. So, therefore, some huge amount of loss is going into the flue gas side. So, so therefore, this is important. This is what how you do exergy energy analysis. So, now we will go to the mechanisms of entropy generation or exergy. This is actually I have covered with the finite temperature difference. Actually, this is a generalized case, but what we discussed is with the individual components of a power plant cycle analysis. This I have already mentioned, S generation should be greater than or equal. So, therefore, Q by TL minus Q by TH. I think this is not really required. These are all this whatever we discussed earlier in the flow destruction due to friction, and this is the irreversibility which is considering heat exchangers and so on. Is a maximum power subjected to the size of constraint, but this is with respect to irreversible, but this actually I have already discussed as a part of previous one, same thing, but in a different format. So, this is the you can see here the power plant model with unmixed hot streams connecting with non isothermal, how the heat So, Th to T out, this is the energy loss here conversion, and if you extend it till dead state, this is what just now we discussed how the energy is lost, Q loss this. So, this part actually we are not considering for any case. So, whatever we consider first law is still here, but second law is still here, that is the difference. So, therefore, work irreversible work is defined with respect to dead state. This maximum power from hot stream has already been explained. Now, we will quickly consider with the flow things same as. So, because those whatever I have explained is considering some case studies, but now you look at how do we do second law for flow systems. This is the first law which you are very comfortable, steady flow energy equation. Steady flow energy is Q minus W is equal to flow C out minus in minus out. So, this is a enthalpy and kinetic energy, potential energy, kinetic energy, these all forms of energies at the exit minus in. Whereas, second law S rod generation, which is given in this, because this is the parameter which we discussed just now, Q surrounding by T surrounding, and here the total entropy generation is must be delta total, that means total change in entropy generation must be greater than or equal to 0. So, whenever there is a Q loss to the surroundings is negative, and it is given as a negative, and entropy generation is the rate of generation for the process. So, now the heat transfer terms, if we eliminate it, this part, if you eliminate in terms of, you write this, then you are writing with the same but additional term here. Actually, I will explain you the potential term. So, you have a reference case here, any point here to any point here, what is the energy difference between these at this we are writing in terms of these two plus these two. These two. So, now the work is given by this first part is same as total energy at the exit or entry, because this is written the other way around. So, total energy at the entry minus Ts T naught Si, that is the Q naught, actually this is the Q naught which we discussed that. So, what is the Q naught with respect, you subtract the energy at the inlet minus Q naught, same way you subtract the exit, then you have a dead state generation. So, here this is the heat loss due to this. So, therefore, the work work produced by the power plant or any flow process or a turbine or any flow process is given by this equation. So, this is actually work done during the process and also useful work of the study. This is actually, you mean to say, here is the actual work done during the process, which is also useful work, since the steady flow device have fixed boundaries and do not involve any work done by or against the surroundings. So, here in the previous case we have considered system boundary, then the environmental boundary. So, therefore, here what is the actual work done within that or within the both system and the environment, that we have to look at. So, therefore, the actual work is only considered with respect to the system boundary. Then, if you have a reversible work, we can obtain by setting the entropy generation term equal to 0. Here this becomes 0, then you will get this. then you can rewrite this for a single fluid, because if there are many, why we have written sigma, because there are many streams are coming in. But now if you have only single stream, then eliminate sigma, then mass flow rates are same. So therefore we can write the reversible work done by the system is the enthalpy minus the entropy change, that is a heat loss due to irreversibility, available unavailable work, plus kinetic energy, the potential energy. So therefore this reversible work is the maximum delivery of useful mechanical power, and I think these are defined in this accumulation non-flow exergy, exergy transfer via heat transfer, this is via mass flow, and where this is released by, that means inlet minus outlet, this is a in, this is out, and here you have change in total energy plus the exergy transfer via heat transfer, because heat transfer is a major source for irreversibility. So then we are coming up with a this dead state condition where V naught is 0 and Z naught is 0. So in this case, then you can write this by A, where A is again available work, which is defined with respect every enthalpy with respect to dead state, then you have heat with respect to dead state, the entropy change also with respect to dead state, and then here V is 0. So therefore no difference, Z is 0. So therefore they are absolute values. So then reversible work for steady flow process is given by the change in availability at inlet minus outlet, that is a reversible work. So this is actually specific availability, that is why you are multiplying mass flow rate. Rate of irreversibility is also associated with steady flow, which is given by reversible work minus, this we have already defined in the beginning, minus useful work, which is defined as the irreversibility in terms of T naught into S entropy generation. So you can find out irreversibility as this T naught into S, which we have earlier defined. I think this we have already discussed, but because why I have put this double, because I thought all these equations we discussed actually, this availability, but the only word this A is extra added into this, all these same terms here, this is the same as this, again repeating this. I will give you some case studies. What we discussed is based on this. How do we write some case study, energy and exergy balance of a power plant cycle. I think I will stop here, we will discuss in the next class, because this is a case study, and meanwhile see we have considered this because the theory part I is initially explained, and then these are after all equations, but the case study means we have taken a power plant. This is a National Thermal Power Plant Corporation, National Thermal Corporation Limited, NTPC steam. These are parameters are considered. It is a subcritical plant. Then so one supercritical power plant is considered, one conceptual ultra supercritical power. These three power plants are considered, and they are studied with respect to energy and exergy, and evaluated those. I will give you that case study in the next class. Okay.